Hello, space fans, and welcome to Professor Britton's Wacky Universe.
You're muted.
Right. Thank you. Thanks, Tony. Good morning, everyone, and welcome back to your last week of lecture for Astronomy 1010. Today, we're going to be finishing up our lecture on the on planetary atmospheres. And if time allows, we'll move into the Jovian chapter and begin studying the gas giants. Our lab for today is on the mass of Jupiter. There's a section up in your lab tab on Blackboard. I've gotten my massive Jupiter printout. Mostly the pages you'll need for that are 6, 15, 6, 7, and most importantly, 6, 5. 6, 5, 6, 7, and 6, 15. We can get to that at lab time when it gets there. Okay, last time we left off with planetary atmospheres, you guys were learning about the layers of Earth's atmosphere and what kind of things happen in the different layers of Earth's atmosphere. So who can do some good remembering with me about the layers of Earth's atmosphere? What have we learned? Let's go to our slideshow here. How do we determine the layers of Earth's atmosphere? What's our criteria? What's the slide that I
fluctuations?
I'm sorry?
Temperature fluctuations and height?
Yeah, temperature fluctuations with height. Very nice. And we can see that we have 4 layers to Earth's atmosphere. Let's remember what they are. The troposphere, where you live. The stratosphere, where ultraviolet light interacts with what chemical again? What chemical is being is absorbing the UV light in the stratosphere?
Ozone.
Ozone, very good. Then we get up to our thermosphere, where X-rays ionize gases and create a little tinfoil layer to our atmosphere. And then lastly, there's the exosphere. The exosphere is where particles leak into space when they are capable of thermal escape. You will remember that last time I taught you that gas particles, obeying an ideal gas, have not one velocity, but they have a distribution of speeds, meaning some move fast. Oh, pardon?
Oh, pardon?
I'm sorry. Are we talking? What's the question? Oh, maybe someone just forgot to mute themselves. I don't know. Anyways, talk to me if you want to talk to me. Gas particles obey a distribution of speeds. Some move fast, some move medium speed, and some move slow speed. And it's not equipartition of speeds. It's a Maxwell-Boltzmann distribution of speeds. That's a sort of statistical distribution that is unique to gases in nature. And it looks a little something like this. Now, I'm worried that in our last class, this was at the end when you were getting mind fatigue. But what this is supposed to be is, this says probability, but what the y-axis really is it's plotting the number of particles that have speed x, which you see here on the x-axis. Maybe I can annotate. Okay, so, well, I don't want to get too sucked into it, but on this axis here, this is how fast the particles are moving. It's supposed to be plotted in bins, although I think they've made the bins quite small here, so they neglected that. And here, instead of thinking about it as a probability, you should think of it as n, the number of particles that have whatever speed you see plotted on the x-axis. you can see that the vast majority of gas particles have a unique, have a unique speed called the thermal speed. I just want to move this little, you guys can't see what's going on, but I'm fighting with the Zoom annotation bar. This speed here is what we call in our class V sub therm. It's the thermal speed. Sorry, I have a hard time drawing with this. Okay, that's the thermal speed. And that means the greatest number of particles travel at that speed. Do you guys remember the formula for that? What's the formula for the thermal speed? It's the square root of 2 times the Boltzmann constant, which is just a dumb number, times the temperature in Kelvin divided by the mass of our gas atom, which could be hydrogen or helium or diatomic oxygen, whatever. Now, when you know this speed, you kind of know how fast the majority of gas particles are moving. And that's a useful kind of metric. It's telling us that the higher the temperature of the atmosphere, the faster the gas particles move. And then, of course, somewhere far up here, there's a cutoff, and that cutoff is the escape velocity of the planet. And I was telling you last time that there's always going to be a few particles up here in the high tail end of the Maxwell-Boltzmann distribution. These gas particles are always traveling fast enough where they can escape into outer space. But of course, once these particles leave, the distribution doesn't now look like this with a hard cutoff. What happens is all the particles smash into each other and they thermalize, as the physicists like to say, and that means they reform the Maxwell-Boltzmann distribution, and they repopulate their high-speed tail with new gas particles that can escape. And that means, at least in the exosphere, gas particles are always leaking into space. We always have a slow leak of gas particles into space. That's okay, because gas particles will be replenished by what geological process? My lovely students, what geological process replenishes the gas particles?
Volcanism?
Volcanism, that's right. Volcanoes make new gas. Okay, and last time we learned that there is a condition. Let's go to speaker view and speaker me. There is a condition for planetary loss. I'm putting this up on the board again because it's kind of important. Or the condition, sorry, not for planetary loss, but for atmospheric loss. The condition for atmospheric loss is if your thermal speed is greater than or equal to 1/5 of your escape velocity, then your atmospheric gas species, like oxygen or nitrogen or whatever it is, then the atmospheric gas is lost, not in 5 minutes, not in 25 seconds, but over a geological time scale. And y'all learned about geological time scales in your office hour session last Wednesday. Does anyone in the studio audience know what a geological time scale is? Let me get my stool here. And I just talking about my chair. What's a geological time scale mean? What's that, like 2 weeks? 15 days?
Is it
How
like
long does it take for something?
Is it like tens of thousands of years?
Think bigger. It's the geological time scale is a time scale over which something interesting happens on Earth.
A million?
Oh, how many?
A million?
More. Is that Kirill?
Yeah.
Hi, Kirill. No, more than 1 million. You worked it out in your homeworks, which I haven't graded, by the way. It's okay. You haven't really submitted them, so we're all in the same boat, right? I think this last week is going to be unpleasant for someone, and I'm starting to get increasingly more worried that that someone is me. Okay, so I'm going to have a lot of homeworks to grade.
Yeah, I have a question. If I just like submit all of the homeworks this week,
I'm gonna fucking
is
hate
it,
you. I'm gonna fucking hate you when you do that. But yes, do that rather than fail my class. But no, Kirill, that I'm going to scratch your name into the side of my wooden desk, and I'm gonna look at it every day and think about how much I hate you as a human being. Okay?
I'm so sorry.
Okay.
Because I do that, and I'm gonna do like the labs too.
Yeah. Guess what, dude? Take some Adderall and have some bloodshot eyes, because you're gonna be up a while. It's gonna take longer to go through that stuff than you think. Okay? You're gonna be in for some long nights, and if you think you can do that, right? But it's gonna be difficult. But okay, whatever. But remember, there's a cutoff, right? Sometime like next Tuesday or Wednesday or something, I'm just gonna submit all the grades and then it's pina colada time, and I'm out. Okay.
Yeah,
So,
no, I screwed up by like just because I didn't have like internet for like a week, and then I was like, oh, like I'm just like not doing anything, and
yeah.
yeah, I screwed up, and
The only thing you've got going for you is I was exactly the same person when I was a student, and I'm actually still kind of that same person. So I have a small amount of sympathy for what you're going through, and I know you're not going to be the only one doing that to me. So just if you could submit a couple of them this week, that would make my life a little less sucky. That would be nice.
I'll just
Anyway,
submit them as I go.
yeah. Hold on. I'm going to just hide the trolls for a second so I can focus on.
Also, I have a question. When
Yep.
do we still have like an exam, or is
As
it?
I mentioned in some of the previous lecture recordings, which you're going to be watching all at once, I'm sure, we've all decided collectively to just double our midterm grade and use our midterm grade as our final grade so that we did not have to take a 3-hour test over the internet. I think everyone was sort of liking that plan. But as I mentioned before, if someone out there really is dying to take a 100-point multiple choice test, I have one, and I can figure out how to submit that to you over Blackboard, but you're gonna have to block off 3 hours, and it's probably not gonna be fun. So if you wanna do that, fine. If you're cool doubling your midterm grade, that's cool too.
I'm good with that.
All right, yeah, that's what I figured. Okay, so what the hell is a geological time scale again? Think of it as how long oh, Laura.
So I might be totally off base. Was it about like the continents moving or something?
Yeah, like how long does it take plate tectonics to reshape the surface of Earth?
Yeah. But I don't know what that amount is, but.
Oh. Kayla, anyone? Nothing, huh?
150 million years.
100 million years. Whoever said that, thank you. That's right. So it's a good thing we had this chat then, right? 100 million years is a loosey. There are different kind of time scales that exist in nature, right? There's the time scale over which a student gets bored, which is usually about 5 minutes, okay? There's the time scale over which something interesting might happen in your life, which is maybe 2 to 3 years. There's a time scale for geological activity, which is 100 million years. Astronomical time scales are in the billions of years. That's how long it takes galaxies to collide or something like that. And there are these different time scales over which something interesting happens. This number comes from a couple of different places. One from plate tectonic time scales, another from the stratification of Earth layers. As geologists study the rate at which bedrock layers get solidified on Earth, 100 million years is a sort of approximate level there. So this is the time scale over which an atmosphere can slowly leak away into space. And of course, Earth and Venus today have large masses and high gravity. Their atmospheric constituents are heavy. And they also seem to have active volcanism, which can replenish these gases. Mars, on the other hand, Mars is a much worse situation because Mars has a smaller mass than Earth or Venus. And its volcanoes, as we saw by studying that Mars MOLA map, have all gone dormant and extinct, and so new gases aren't replenishing the atmosphere of Mars. One last thing that we ought to throw in there is Mars lacks a global magnetic field, and it turns out that magnetic fields have a big role to play in planetary atmospheres. Now, up to now, I've been putting this discussion off, but let's just take a hot moment here to talk about magnetic fields. In my planetary geology slideshow, which I think is here, I had just two little cartoon pictures to help you understand how a magnetic field works. Bear with me here as I hunt for those little pictures. Here we go. So let's talk about slide 32 here for a second. I want to talk to you guys about a kid's toy called an electromagnet, okay? You guys might remember that in our lecture on the sun, we learned some rules for magnetic field generations. And one of them was, if you take a wire and send a current of electricity, which is flowing electrons down that wire, you will generate a magnetic field in the form of a circular loop that wraps around your wire. If you were to attach a wire to a simple 3-volt battery like this D battery here, you would get a weak current of electricity and therefore a wimpy-ass magnetic field. However, if you were to wrap your coil of wire around a ferromagnetic metal, such as a lump of iron, iron is not by default magnetized, but it is ferromagnetic, which means it is capable of becoming magnetized in the presence of a magnetic field. So as we wrap our coil of wire around this lump of iron, we kind of generate a little solenoid here, and the wimpy magnetic field passes through the metal, which then magnetizes all of the little electron currents in the iron block here. And the wimpy magnetic field turns into a stronger magnetic field because you're intensifying its effect by using the little magnetic field to magnetize this lump of iron, and then it becomes more powerful. Now, I can think of another place where we have a current of charged materials circulating around a lump of iron, and that's the center of Earth. Hold on, click. Sorry, all of my scribblings here are getting in the way. So let's X out that. There we go. Now, the formation of a geomagnetic field, the dynamo effect as it's called, it's pretty complicated, and it's not quite as simple as this, but if we want to just tell you a simple story, you will remember that Earth has a layer of solid iron in the core, and the outer core is a layer of liquid iron, which is no doubt stupidly hot and probably exists at some fractional layer of ionization. Not all of those atoms are going to be completely neutral. Some of their electrons will be stripped off. So as the Earth spins on a 24-hour rotation period, that warm liquid iron, which is partially charged, is sloshing around your lump of iron in the core, and you basically turn Earth into a giant ass electromagnet. And perhaps we could codify this by writing down 2 rules for planetary magnetic fields, 2 basic rules. Okay. So 2 rules, or the 2 conditions, let's call it the 2 conditions for a planetary magnetic field. 2 conditions for a planetary magnetic field. The first is a hot interior. We're assuming the cores of most of the terrestrial planets, or all the terrestrial planets, are iron and nickel. Hot interior, preferably with a liquid metal core. And the second condition is rapid rotation. And what rapid rotation means is something like Earth's rotation. So somewhere between 1 to several days. Or less. Let's take a moment to see what you guys know about the solar system, and let's predict which planets in our solar system have magnetic fields. So I'll go to my share screen here, and we'll look back at our early slide. Here we go. Okay, so which of these buggers are going to have a magnetic field? Let's start with Earth. Does Earth meet these 2 conditions? I'm starting off with a softball here, guys. So Earth has a powerful geomagnetic field, right? If you've ever used a compass, you know that. How about Venus? Can Venus have does Venus have a magnetic field?
Doesn't it not rotate, or is that Mercury?
Well, a little of both, but Venus is especially slow. You will remember that the spin period of the spin of Venus is something like 243 days or something like that, where its orbit around the sun is 220 days. So a day on Venus is longer than a year on Venus. Venus is rotating so slowly that it's effectively not rotating at all. And because of this, despite having a big fat planet with a hot liquid metal core, it doesn't have a magnetic field at all. And that's turned out to have a profound effect on the history of Venus's atmosphere, as I will reveal in time. How about Mars?
Yes.
What's the rotation rate of Mars? Anyone know?
Isn't it just a little slower than Earth?
Yeah, it's basically the same. I think it's like, actually, I think it's a little faster. I think it's like 23.5 days or something. It's almost identical to Earth's rotation, which is kind of amazing. However, Mars lacks a geomagnetic field. Why?
Core's not hot enough?
Yeah, you can see by the depth of its lithosphere that the internal heat of Mars has been lost. On the other hand, you know, we have these rovers like the Curiosity rover traipsing around the surface of Mars. Many times we have taken rocks, and you can actually study the magnetic history of planets by looking for magnetization in tiny flecks of iron in the rocks. And we can see from studying the magnetization of rocks that Mars in its past actually did have a magnetic field when its interior was a bit warmer. I should just say something about this as well. The history of Earth's magnetic field is actually quite complicated and interesting. You guys will remember from our planetary geology lecture that planets undergo something called seafloor spreading. Let's get a quick picture of seafloor spreading. It's related to plate tectonics, and it's also kind of related to volcanism. It's where we see places along the mid-Atlantic ridge pumping magma up to the floor of the seabed and adding to the seafloor in the form of warm convective rock. Well, when this rock is warm and molten before it solidifies, it actually records a little history of the Earth's magnetic field. So you can send a trawler down to the bottom of the ocean and you can sample the rock bed along this Atlantic seafloor, and you can get a record of the Earth's magnetic field. And if you do this, it turns out that Earth's magnetic field has not always maintained the same polarity, but it's flipped back and forth over geological timescales. But the planetary science mystery that we still don't know the answer to is what causes these flips in the magnetic field, because they're not periodic, they're aperiodic or chaotic. History of Earth's geomagnetic field. I just want to show you a Wikipedia slide here that's pretty cool. Let's see if I can find this. It's a graph of the number of flips of the Earth's dipole. Let me just go to images here. It's basically, it looks something like this. Let me type in, I'll tell you what, let me type in geomagnetic reversal. You have to use the, yeah, here we go, geomagnetic reversal. Hopefully this will have, this is what I want right here. So look at this totally fascinating graph showing you the history of Earth's geomagnetic reversal. Let's see if we can get a nice large picture here. Now this is in mega annums, right? So a mega is 10 to the 6. So this is over the last 5 million years. And you can see sometimes there'll be periods of, 100,000 years. Sometimes it'll just be 1,000,000 years. Sometimes it'll be any number of times. But the Earth goes through these chaotic flips in its magnetic field where the North Pole is at the North Pole, and then suddenly the North Pole points down at our geographical South Pole. And so trying to understand these flips in a planetary magnetic field is an ongoing area of research in planetary science. Yes, Jace?
Are these changes gradual, or do they happen instantly?
They do not happen instantly. They take time, but I believe the times, so, all right, it would help to know exactly what's being plotted here. My interpretation of this is it's black versus white, and when it's black, North Pole is pointing up, and when it's white, South Pole is pointing up. I should mention too that it's a little confusing to talk about because you know how all our North Pole needles point towards the geomagnetic north? That means magnetic south is at our geomagnetic North Pole. So it's already kind of confusing because we define north as whatever the North Pole of our magnet points to, right? But North poles of magnets are attracted to magnetic south poles. So talking about this can be goofy, but Jace, I believe the answer to this question is it happens fast compared to millions of years, but not fast compared to a human timescale. So let's say it might take 5,000, or I'm kind of making this up, but if I had to guess, it would be 5,000 or 10,000 years to flip, and then it will stay. The problem of talking about this is there is no coherent period to how long the poles stay aligned. This is what's fascinating about it. This is what makes it asynchronous. It's not a uniform time period like it flips every 10 million years or every 100 million years. It'll flip for 10,000 years, and then it'll flip for 150,000 years, and then it'll flip for 1,000,000 years. And people don't understand what chaotic mechanism is causing this. It's not simple. It's not periodic. Anyways, you can read about the whole thing, and you'll probably know more than me if you read this wiki page on geomagnetic reversal. I think the point I'm trying to make, the larger point, is that magnetic fields for planets change over time. Sometimes they get weaker, sometimes they flip. But it turns out that having a magnetic field is so important for the health of a planet for reasons I will discuss in a moment. Now, let's finish the job here. Is the moon going to have a magnetic field? No. How about Mercury? You'd think that Mercury wouldn't have a magnetic field because its lithosphere is medium thickness and it's kind of small and cool, but it turns out that once again, what makes Mercury perverse is it has an obnoxiously large metal core. And because of this, while Mercury's magnetic field is hundreds of times weaker than Earth's, it is a little more significant than planets like Mars or the moon. Mercury has a slight, wimpy, weak magnetic field, and planetary scientists go nuts studying the magnetic field of Mercury. So I'd hate to lie to you and tell you that Mercury's devoid of a magnetic field, but it's so wimpier compared to Earth's that it almost doesn't exist at a first blush look. So what does a magnetic field do for me, and why am I learning about it? We're learning about it because of ways that atmospheres get lost to space. Let's go back to this slide here, slide 36. You'll remember that there's lots of ways for atmospheres to leak away into space or to chemically react with the surface. But in the upper exosphere of a planet, not only do gas particles just leave their planets because of their Maxwell-Boltzmann distributions of speeds, but they get helped along by a process called solar wind stripping, where solar wind ions traveling at close to the speed of light smash into gas particles and give them enough kinetic energy to jump off the surface of the planet. Well, a planet's magnetic field is a bubble which protects against this. We call Earth's magnetic field its magnetosphere. So here's a picture of Earth's dipole. And oftentimes, let's see if I should have a better picture of this somewhere. This picture here kind of shows you a cartoon of what's going on. Earth's magnetosphere, its magnetic bubble, gets actually pushed back and blown like hair in the wind by solar wind ions that are leaving the sun constantly. But the magnetic fields capture charged particles and slough them off to the sides which reduces their ability to pummel our atmosphere. In fact, in most cases, the kinetic energies of the particles get strongly reduced and they just kind of make a cool laser light show that we call the Aurora Borealis. But on Venus, instead of having a magnetic bubble protecting your planet, these solar wind ions are smashing into your air particles or your gas particles, and they're busting them apart and kicking them into space. This is especially true for water molecules, which we believe have been damaged over time by Venus's magnetosphere. Today, this week's homework is going to give you a legendary problem in planetary science explaining that. Okay, I want to have a thought question for the class just to see if you guys can sort of understand some tricksy things here. I want to show you a picture of the Maxwell-Boltzmann distribution of speeds. And I want to talk about those gas particles which are moving fast. And I want to go back and I want to look at the layers of Earth's atmosphere. F525. Class, the Maxwell-Boltzmann distribution of speeds. Oh, I'm sorry. You guys, I don't think you're seeing my screen right now. I don't see that little share screen icon. Hold a second. Okay, here we go. If I show you slide 25, why can't gas particles that are traveling above Earth's escape velocity leave the planet when those gas particles are located in the thermosphere? Here, we have some high-speed gases, and they can bleed out into space. Here, we have a small fraction of high-speed gases. They cannot escape into space, nor can gas particles in the stratosphere, nor can gas particles in the troposphere. Why not? Why can they only leak away to space here in the exosphere?
Could it be because the temperature drops in the thermosphere? Maybe the cold slows them down?
Well, all right, that's a pretty cool answer. I suppose you've got a point, Kayla, that if the temperature is going down, then the entire Maxwell-Boltzmann is contracting. And that's not wrong necessarily, but there's a more pressing reason, and it's got something to do with this cartoon here. The density of particles in the thermosphere is higher than in the exosphere. Okay, well, maybe this is just too much. Maybe I've either worded the question unfairly or particles of gas have something called a mean free path. A mean free path is how far can my gas particle go before it bumps into a neighbor. Now, the denser the gas is, the shorter your mean free path is. I think gas particles in the troposphere collide like 10 to the 20 times a second. It's something absurdly ridiculous. Collisions are happening so often that gas particles can only travel a short distance before they random walk their way around through the gas. And collisions basically block them. That's what I'm trying to say. I'm trying to say something simple, and I'm making it complicated. Collisions block your gas particles. So here, to use some technical mumbo jumbo, let's go to, sorry, slide 25. Here, oh, I don't know what that was. Here, the gas particles are of such a low density that the mean free path allows the high-speed atoms to escape into space. But here, even if you have some high-speed atoms, they might be traveling at 12 or 13 kilometers per second, but they can only travel a few meters before they smash into another particle and get deflected in another direction. So you can only have gas particles escaping at your exosphere because that's where the gas is thin enough for people to exit the mosh pit, okay? Here, the mosh pit of gas particles is much too dense for you to simply walk out of the pit, okay? I want to talk to you guys. I actually want to have a little bit of fun since it's our last week here. And I want to think about what it means to discuss layers of an atmosphere above 40 kilometers or so. Have you guys ever heard of the Red Bull Stratos mission, where that Evel Knievel guy, the Felix Baumgartner, he kind of did this stunt where he took a a balloon up into the stratosphere, and he did the world's longest free fall jump, no, I guess a parachute jump down to Earth. And it's pretty amazing to take a second here and just peek at the Wikipedia page for that. I think you guys will get a kick out of this. Maybe we can even watch a second or two of the video. So let's take a look at how high Felix Baumgartner got up here. Let's look up Red Bull Stratos, and I'll show you a clip from the video in a second, but it's, oh, excuse me. So on the 14th of October, Baumgartner flew to 39 kilometers into the stratosphere over New Mexico, United States, and he did a free fall jump where he jumps out of the little capsule, and the whole thing took maybe 20 minutes or so. Oh, sorry, even less. The whole jump took 10 minutes, okay? And I want to show you a picture from the moment before he gets out of his capsule here, because of course they had cameras and recorded the whole thing. So here's the moment that Baumgartner is about to step out of his capsule. Now keep in mind here that if we compare this to our layers of Earth's atmosphere, Baumgartner, this is slide 25, right? Click function F5, 25. Baumgartner is like, he's like here. If he was 39 kilometers, this is how high he went up. He wasn't even at the top of the stratospheric bump, right? But if you actually look at the picture, let's erase, oops. Sorry guys, I'm still trying to master the art of drawing on my slides here. It's kind of fun, but I'm not particularly good at it. I don't know about you guys, but this shit looks like outer space to me, right? Like he's got a space pod, and he's got sorry, I'm just looking for my pointer mouse. Oh, I see. It wants me to zoom in. He's got like a spacesuit on, you know? And you can see the curvature of Earth, and the sky is no longer blue above its head, it's black. He could probably see stars. Any one of us, had we been up there with Felix Baumgartner, we would have considered ourselves morally and ethically in outer space. And yet, there are still gas particles here which have a meaningful effect on the physics of Earth. Now, just because I know you guys will enjoy it, and it's a fun thing to do to waste some time today.
What about the capsule? Did they just like leave? Did they just like sacrifice it? It was just the one mission.
Yeah, I'm guessing that they just, what would happen is if you left the capsule at some orbital height of 36 kilometers, or sorry, 39 kilometers, it would get orbital drag from, even though it looks like outer space, there'd be trace amounts of gas particles slamming into it, and that will cause the capsule to slowly lose altitude and then plummet into Earth's atmosphere and burn up. So I'm guessing they weren't worried about it because they knew that it would slowly descend into Earth's atmosphere, and as the density of gas increased, it would burn up. Now, I think it's actually worthwhile to take a moment here, Red Bull Stratos. Obviously, this would be cooler if we were all in class together, because I'm sure this is going to look glitchy and crappy, but hold on a second. They have the whole thing on YouTube, like the whole 10-minute journey. Hold on, where is it here? Red Bull Stratos jump full. Here we go. Okay, now hopefully,
there it is.
are you guys getting the sound here? Can you hear the
door
machine
has
control
opened.
talking?
Roll the door open.
Okay, let's just watch this because I think it'll be interesting. I actually don't have a full 10 minutes to burn, but I have a few seconds to burn. At least we can watch where he jumps from the capsule. And hold on, I'm just trying to move my slider around where it won't interfere with my discussion. Let's take a look to him, that moment where he kind of gets out of the space pod and just does his jump. Now, one of the interesting things I understand about this is the particle density of air is so low at this altitude that this jump was extremely dangerous and life-risking, because he had to perfect this perfect little bunny hop because if he jumped clumsily out of the capsule and gave himself any small amount of rotation, the rotation would continue to the point where basically G-forces would slosh all the blood to one part of his brain and he would lose consciousness and die. So he had to make sure that he didn't give himself too much angular momentum because there would be nothing to stop his spin. And as you're about to discover, he did, despite practicing this graceful fall, he did end up getting a little bit of rotation and lost consciousness for several minutes before he hit the heavier density air in the troposphere. Also significant is he actually achieved a world record, and I believe his free fall accelerated him to the point where he traveled faster than the speed of sound. So he actually went past Mach 1 during the descent. Now I'll show you guys a couple of minutes of it here because I think you'll just get a kick out of it. Let's watch that little bunny hop
And
here.
our guardian angel will take care of you.
He mumbles some stuff.
All your
Here we go. Look at that.
Woo!
Now, his angular size is going to be so small that they're not going to have good resolution, but you can see his little body spinning out of control there. And at some point he stops breathing and he loses consciousness. I believe they plot his speed too at some point. Oh, here we go. So he's already traveling at
Speed 546.
500 kilometers. I'm sorry, 500 miles per hour, 1,000 kilometers per hour.
Speed 650 miles per hour. Speed 700.
Now, what's interesting is
Speed 700.
as he starts to
Raise your hand.
oh, question?
Tell him what you said.
In the video, he does have a camera on him, and I have seen that video.
Oh, so you can see it spinning around?
Yeah.
You can see he's got a
He
whole
spins out a little bit.
Oh, that's cool. I didn't know you saw it. That's awesome. Yeah, so he's definitely spinning a bit. You can see everyone's kind of silent here because he's got a little mission control down in Roswell, New Mexico, and they're all wondering if they just killed this guy, right? Because he's lost consciousness. But as he hits the troposphere and the particle density increases, he can use that to slow his rotation, and that allowed him to come back with it.
Why is there an Austrian flag at the mission control?
That I do not know. I missed that.
He is Austrian. Baumgartner is Austrian.
Oh, okay. Thank you for whoever explained that. Here's his rotation slowing down. I didn't realize you guys seem to know more about this than I do. I didn't realize you guys had all seen this. That's great. Anyways, you get by the way, just to think about the whole damn thing, we'll skip ahead. It takes about 10 minutes. And 10 minutes later, he just plops down in, like, what a journey. This guy actually got to travel through 2 layers of our atmosphere, right? And if you kind of...
closer shot from the helicopter.
Where are we here?
So how did he regain consciousness?
I think once the rotation stopped, he stabilized himself. There was a moment where they all start clapping, but I couldn't find it. And that's because they his vitals. But look at this. He not only regains consciousness, but he lands on his damn feet, right? Like, that's pretty amazing. Now, imagine getting to be this dude, and imagine getting to travel through these layers of our atmosphere and experience that. That must be, like a pretty special experience. And I'm sure there'll be more Evel Knievel stunts like this to follow. Okay, now that we've talked about this, you realize that most of the gas in a planetary atmosphere is actually located in the troposphere. Once you get above the troposphere, you're talking about very small quantities of gas. So now I want us to take a look at how things work inside the troposphere and learn about how planetary atmospheres are heated. So we made a small point in our last lecture about the fact that our planetary atmosphere is transparent to visible wavelengths of light. And that means visible wavelengths of light penetrate all the way down to the ground and they heat up ground rock. That means our troposphere is not being heated by visible light. It's being heated by infrared light coming from below. And the types of gases that are responsible for doing this are called greenhouse gases. They're particular gases that are good at absorbing infrared light. And here's a little animation of that. We have some infrared photons that come along and strike a molecule like carbon dioxide. Can I do this animation? The infrared light is absorbed by the molecule. It causes the molecules to vibrate and jiggle. And then after a time, they will re-radiate their infrared light at a slightly longer wavelength, and it'll eventually work its way out of the atmosphere. The only problem I have with this GIF is that the whole thing should happen upside down. The photon should come from below, and the escaping radiation should head upwards into outer space. So let's take a couple of notes on the greenhouse effect and greenhouse gases. Okay, so greenhouse gases are basically gas molecules that are very effective at absorbing infrared light. Most of Earth's atmosphere is composed of what constituents, class? What's the composition of Earth's atmosphere for the most part?
Nitrogen.
Thank you. Was that you, Morgan? Who was that?
I said nitrogen.
That was Jillian.
Oh, Jillian. Okay, sorry, you're a little garbled, but okay. And Lucas, I missed you saying it. So nitrogen is 77% of our atmosphere. That's not a greenhouse gas, nor is oxygen. Greenhouse gases include things like CO2, a very powerful greenhouse gas. CO2 has 2 oxygen atoms bound by little springs to a carbon atom. These molecules have vibrational modes, and they can vibrate in a number of different ways. The carbon can ping pong and boing boing back in between the 2 oxygens. They also have bendy modes, where the oxygens and the carbons can kind of seesaw with each other. The oxygens can vibrate. Every time you hit one of these things with an infrared photon, the infrared photon gets absorbed and the molecules get some internal energy and bounce around. Another key greenhouse gas that people always forget about, water. Water is a potent greenhouse gas. Those clouds that you see, they block sunlight, but in terms of infrared photons, they make things warmer. What percentage of Earth's atmosphere does CO2 and H2O comprise? That would be good to remember here. Other greenhouse gases include methane, which primarily comes from agricultural products, meaning cow shit. What else? There are some others, but CO2, H2O, and methane, these are some of the more important greenhouse gases in our atmosphere. I think nitrogen dioxide is another one, but they get increasingly smaller in terms of their percentage of Earth's atmosphere. I was hoping that you guys might remember what fraction of our atmosphere CO2 and water comprise, because that's kind of important for this discussion here.
It was like 0.4% and 0.04%.
Yeah, which is which? Well, that's good enough for me. It's 0.4% water, 0.04% CO2. Now, these gases comprise less than 1% of our atmosphere, but as you're about to discover, play a big role in keeping our planet warm and livable. Okay, let's look at a little cartoon of how the greenhouse effect works. And I don't know, maybe we'll take notes on it, maybe we won't. I'll see how I'm feeling. I want to show you a little cartoon here. F542. Okay, so the way the greenhouse effects works is those gases, which have only trace abundances in our atmosphere, play a big role in heating up our planet. So first, what we have at the bottom here, or sorry, let me get my annotator out. So here comes some visible wavelengths of light from outer space, red, green, yellow, blue photons. They strike Earth, and they heat Earth's surface rock up to an average global temperature of, like, I don't know, 15 degrees Celsius is 15 plus 273. So it's maybe 288 or 290 Kelvin is close to the average global temperature of Earth. And while that's not particularly hot, it's warm enough to consider the surface of Earth a black body. Black bodies, as you know, re-radiate photons somewhere around 10 microns. And these infrared photons start moving up through our atmosphere, but they get captured and absorbed by greenhouse gases like CO2 or water. Those gases vibrate around and they mosh pit into their neighboring gas particles, heating up the atmosphere, and then they re-radiate photons, which eventually leak their way into space. This has the effect of heating up our planetary gases and keeping them warmer than they would ordinarily be. And the greenhouse effect actually has a pretty potent role on planetary temperatures. Let's take a look at a couple of different planets and see what effect the greenhouse gases have on them. I've got a little graph here, and I want you guys to take a look at this because it's very interesting. On Earth, let me just get my annotator. It tells us that without the greenhouse effect, Earth's global temperature would not be positive 15 degrees Celsius, but would be negative 17 degrees Celsius. Now, that would be a cold and unpleasant planet to live on, one which was 30 Celsius degrees or close to 60 Fahrenheit degrees colder than it is today. Imagine if global temperatures dropped by 60 Fahrenheit degrees. I'm sure the ice caps would increase. I don't know if all of the oceans of the Earth would freeze over, but I'm sure that the ice caps would be significantly larger than they are today. We might even put ourselves into a sort of snowball Earth phase, or a global ice age. That means we are getting a net temperature differential. Now, they screwed up here in the book. They should have put the degree symbol afterwards, of 32 Celsius degrees worth of temperature change due to the greenhouse effect. And that's coming from gases that make up 0.5% of our atmospheric gas. Just imagine going to a place like Venus. Venus's atmosphere is 96% carbon dioxide. So while its average global temperature, all right, this is a little bit confusing. They have the average global temperature at minus 43 degrees Celsius, which is awkward because Venus is closer to the sun. It should be warmer than Earth. In any case, today Venus's average temperature is 470 degrees Celsius, meaning Venus gets a whopping 500 Celsius degrees worth of temperature change due to its runaway greenhouse effect. Class, let's take a look at Mars. Like Venus, Mars has a 96% CO2 atmosphere. But Mars is only getting a 5 Celsius degree temperature change. Why? Mars and Venus have the same composition to their atmosphere. Why wouldn't Mars's atmosphere also produce a runaway greenhouse effect? Anyone know? Simple answer. Let me make sure you understand the question. The composition of Mars's atmosphere and the composition of Venus's atmosphere are the same. They are 96% CO2. That means their entire atmosphere is greenhouse gas. On Venus, this creates a runaway greenhouse effect with a 500 degree temperature change. Here, it creates only a 5 degree temperature change. Why is it so dramatically different on these two planets?
Because Mars was already so cold.
Well, but okay, Mars is going to be colder than Venus because it's farther from the sun. But the temperature differential should be similar in theory. except it's not about Mars being cold. No. It's just that Mars's atmosphere is much thinner than Venus's. There's less gas to do the greenhouse effect because the atmosphere is thin there. Anyways, I thought we should address that. Okay, why don't we take some notes? I want to introduce to you guys a new formula. Before we talk about the greenhouse effect, let's just imagine a rock in space that's being heated by sunlight, okay? There are three things that affect the temperature of a planet, and we're going to take these as notes because I think this is a noteworthy enterprise. Why is my planet hot? Okay, this is the question we're addressing. Why is my planet hot? There are three things. The first is your distance from the sun. And we're going to be measuring this distance in astronomical units in the upcoming equation. The closer you are to the sun, the more radiation you absorb. The second thing that affects how hot you are is something called your albedo. I mentioned this before, but your albedo, which we'll give the symbol A for, is your percent reflectivity of your planet's surface, where an albedo has a domain of anywhere from 0 to the number 1. An albedo of 0 would be a perfectly black substance. Basically, the definition of a black body. You only absorb radiation and you only re-radiate it because of your temperature. A perfectly black planet would have an albedo of 0. An albedo of 1 would be a perfectly white planet, or maybe even more appropriate, we could think of it as a disco ball. A disco ball has an albedo of 1. It reflects all the photons that are incident upon it. The third thing is the greenhouse effect. Before we study the greenhouse effect, I'm going to introduce to you a formula that helps you determine how warm a piece of rock in space should be based on distance from the sun and albedo. And this actually is a more useful formula than you at first might anticipate. It can teach you a lot about how the solar system works. Let me just show you a slide screen of some different albedos so that you guys have a sense of, a sort of gut level sense of how albedo works. So down here you can see some various substances on Earth and the average albedos associated with them. Fresh snow could have an albedo of 80 to 95%. If you've ever gone outside after a snowstorm and needed to put on your sunglasses, there's a good reason for that, which is the amount of light you're getting from the ground can be comparable to the light you're getting from the sun. And you can get, what do they call it, snow blindness? Grassland and crops, they can be up to 25 or 30% albedo. Maybe you've heard that it's always warmer in the cities during the summer. That's because the cities are covered in concrete and asphalt and blacktop, which can be as low as 5 to 10% albedo. Here's an interesting one. 2/3 of the Earth's surface is in the form of water, and water's albedo can dramatically vary from 10% to 60% depending upon the altitude of the sun. Anyone who's spent some time down in Newport Harbor with your sailor friends know that they need to use very expensive polarized sunglasses because during sunrise and sunset, when the angle of the sunlight is shallow, the water can become every bit as reflective as a mirror and can blind you and cause terrible headaches from the light that strikes your eyes all day. Let's talk about the moon for a second. What color is the moon when you look up at it on the sky? What color is the moon?
Gray.
This should be a simple question.
Gray.
Okay, gray, white. It looks white on the sky, but it looks gray when you see photographic pictures of the Apollo astronauts. But Kirill, according to this slide, what's the closest substance on Earth to the moon's average albedo?
Asphalt.
Yeah. The moon's surface is actually black volcanic rock. And I just want to show you guys something here. I want to show you a picture from that Apollo landing series again. And well, first, Kirill, do you understand why it looks gray in the photographs when it's actually the color of volcanic rock or dark black volcanic rock? Does that make sense to you, or does that seem weird?
Because the camera just like it removes any like unnecessary reflection from the sun.
I don't know. It's that. It's kind of a simpler thing in contrast photography. Imagine going to the beach on the sunniest day of summer when you're walking out onto the beach and the sun is so bright and so intense that you can't even see without sunglasses or without getting underneath an umbrella. And imagine that sunlight beating down on the sand. Now, you're still under the protective layers of Earth's atmosphere, which absorb 2/3 of the radiation across the EM spectrum and especially block out ultraviolet light. Now imagine standing on the surface of the moon. It would be dozens of times more bright than the sunniest day you've ever experienced at the beach. And even though this moon rock is dark and black, you're getting so much sunlight beating down on it that even the 5 or 10% that's reflecting off the surface is actually it's kind of like a grayish whitish light. But when you take these rocks back to Earth and you look at samples, oops, sorry, I didn't mean to stop the share. I meant to change the share. When you look at some of these lunar rock samples, some of them are jet black. So here's a picture of a rock sample. This is basalt rock. This is black volcanic rock. So the surface of the moon is actually quite dark. Ooh, that's a nice high-res picture of some moon rocks there. Okay, there's a formula that allows us to compute the temperature of a planet, and it's based on basically using the inverse square law and the Stefan-Boltzmann law together, but I'll spare you the details and get to the point. There's an important formula in planetary science known as the no greenhouse temperature. And it answers the question, how hot is my airless rock, like the surface of Mercury or the moon? How hot is my airless rock due to sunlight alone? No greenhouse effect or no atmosphere being included. And that temperature can be computed from 280 Kelvin times the 4th root of 1 minus the albedo divided by the distance squared. Okay, A here is your albedo. It's a number from 0 to 1. And D is the distance to the planet in astronomical units. And believe it or not, an extremely interesting sample problem to try, is to try one based on the moon, okay? So let's do a sample problem. Oh, sorry. I'm writing funny things here. Remember that the moon has no atmosphere. So when I ask you how hot is the surface of the moon, I'm saying, what if you foolishly took off your space glove and you just pressed your hand down against the lunar regolith? How warm would the surface of the moon rock underneath your feet be? So what should we use for our distance to the moon?
The distance from Earth, 1 AU.
From the sun, 1 AU.
Right.
I guess I should have put that here. How How about the average albedo?
That be the 0.6 or 0.8?
Okay. Let's, just because I know the answer will come out cute, we're going to use 0.7, which is right in the middle. Is that okay, Tony? 0.6 was very reasonable guess, though. It'd probably have the same result. Okay. Okay, so
0.07, I think, Professor Britton.
Yeah, what's that?
0.07, I think.
Oh, thank you, Zaz. Oh my gosh. Yes, I was about to make a big whoopee-doo there. Okay, that was last night's whiskey talking right there. Okay, 0.07. Thank you. All right, let's punch them up. 280 Kelvin times the fourth root of 1 minus 0.07. Probably ought to put that in parentheses. Actually, it's just being divided by 1 squared. So let me walk you through the punching of this, because this could be an adventure for some of y'all, okay? Got your Casios ready? We're going to do 1 minus 0.07, and then we're going to hit equals. Now, to do our fourth root, we have to do shift x to the power of 1 over y for equals. That gives me 98%. And then I'm going to back multiply it by 280. And what do you get? 3 sig figs is fine. Hey, Jordan, could you turn the temperature down a little bit? Thanks.
275.
Yeah. And units? I didn't really discuss them, but I was hoping it'd be obvious.
Can you walk me through the fourth root again? Sorry.
Sure thing. Okay. Jace, the fourth root is the same as the power of 1 over 4. So it's the orange menu above x to the y, right? So I'll do 1 minus 0.07 equals 93%. Shift, and then hit your x to the y key. And then you have to hit 4 to let it know it's the fourth root. And then you have to hit equals. Did you get 98%?
Yes.
Awesome. And then you times that by 280. Hey, this is 275 Kelvin. This answer, like many problems I do with you, has a point. This is not a random number. Why isn't it random? Why does that number seem interesting to me? Why is it fascinating that the surface of the moon should have an average temperature of 275 Kelvin? That's really close to another number. That's interesting. Oh dear.
Wasn't it the average temperature?
For like a freezing point?
Oh, who said that? Was that Jillian? You smarty pants. Hold on a second. What would that be in Celsius?
It's like about 1 degree.
Or 2, I think it's 273 is 0 degrees, right? 273 Kelvin. 273 Kelvin is 0 degrees Celsius, right? So that's 2 degrees Celsius. Why would I find that? Why is that an interesting answer from the point of view of planetary science? You know, Earth didn't look like Earth looks like today when the solar system first formed. If you want to know what Earth looked like, let's get that picture from Heavy Bombardment again. We need some illustration from our weed-smoking artist friends, okay? When Earth first formed, it probably didn't look like the Earth we know today with green and brown continents and and a blue sky atmosphere and water clouds, it probably looks like the surface of the moon. It probably just looked like volcanic rock, except the only difference between the way the moon looks and the way early Earth looks is early Earth would have had active volcanism and cracks along its surface. It probably would have looked similar to the planet Vulcan in Star Trek, if you know what that is, right? It would have looked like a volcanically active world that was covered in black volcanic rock and had lava pouring out everywhere and some cracks. But man, isn't it interesting that the temperature of that rock would just be a little bit above the freezing point? Now, what I'm telling you is a little bit of a lie, because it turns out that in outer space, 0 degrees Celsius is not the freezing point of water. It's closer to 160 Kelvin. But probably Earth would have had some weird atmospheric gases around it, which would give it a tiny bit of pressure. So perhaps, who knows, perhaps with a little bit of atmospheric pressure, certainly as those gas particles built up, it's interesting the temperature of that rock would be pretty damn close to the freezing point. Now go with me, my friends, on a little mind journey about what would have happened in early Earth. On slide number 80. So, oh shoot, I have a feeling like you guys cannot see me right now. Just a second. Share screen. Sorry, I'm too fast for the machines, guys. They can't keep up with me. So let's go to slide 80 here. Function F5, slide 80. Bam. And let's minimize your little faces. Okay. So look, here's a picture of what early Earth is like, all right? We have volcanoes, and the volcanoes are pumping out water, carbon dioxide, maybe some sulfur dioxide. And as they start to build up an atmosphere, you're getting a bit of gas pressure, and you're just above the freezing point of water. It's just warm enough where some of that H2O is going to condense and form some salty oceans. It turns out that these salty oceans are really useful to us, not only because we like to drink water and all that, but because they trap carbon dioxide. Unlike Venus and Mars, which just were stuck with all of their CO2 in a gas form, our liquid water oceans could absorb CO2 dissolves in water. Ever enjoyed a bubbly glass of Coca-Cola before? All of those bubbles are carbon dioxide. Or maybe if you like polar seltzer, like I do. Those seltzer bubbles are made of carbon dioxide dissolved in water. And once you dissolve some CO2 in water, you can form sediment and carbonate rocks at the bottom of the seafloor, which basically pull carbon out of our atmosphere. That carbon gets sloughed along in subduction zones by something called the CO2 cycle. This is the next part of my lecture. Venus, on the other hand, kind of got porked over, because at 70% of an AU, it's a little bit warmer, and instead of condensing some of that H2O into liquid water, all of that H2O is going to get stuck in the gaseous form in the form of steam clouds, and then without its global magnetic field, you're going to bust all of those water molecules apart, and the little OH ions are going to combine with sulfur dioxide to make those evil acid rain clouds that melt spacecraft on the way down to the surface. Now, we know more about the surface of Mars than we do about Venus, because Venus's atmosphere is so thick and its atmosphere is so toxic due to these acid rain clouds that any spacecraft that you attempt to land on the surface just melts and dissolves instantaneously. And I've got one picture of the surface of Venus, or one or two pictures, that I'd like to share with you here. In fact, I can't believe I haven't done this already. The Russians during the 70s and 80s made a number of unsuccessful attempts to land on the surface of Venus with their Venera spacecrafts. Eventually, they did manage to get down to the surface. Slide 123 will show you a little picture of their. Now, check out this amazing photograph from space history here. Here we can see the Russian Venera 12 or 13 mission. This is one of the ones that made it down to the ground. And they had a sort of mothership that dropped a probe down to the surface. The probe only lasted several minutes before it just succumbed to the high temperatures and pressures of the atmosphere. But if you want to see the pictures that they actually got, This is the picture just a few moments after landing on the surface of Venus. Now, if you guys can see that little cap there, that's basically the lens cap to the camera that just popped off of the camera and is now dissolving in the toxic atmosphere of Venus. You can actually see the spacecraft, the metal, starting to get corroded and eaten away at the surface by the acid rain clouds. Now, if you reconstruct and make a three-dimensional image of the pictures that the camera took, the world that you see on the surface of Venus is just slabs of volcanic rock and extremely stagnant atmosphere. There's no mountains, no valleys, no tectonics, just slabs and slabs of basaltic rock, just sort of cooking in the high temperature environment. Because Venus has no rotation, there's not even cooling gusts of wind to cool the planet down. It's just a stagnant temperature. I mean, think about it. On Venus, the temperature of the equator is the same as the temperature of the North Pole because convection is so good at mixing their atmosphere. So it turns out that having some liquid water on your surface is really good for producing an atmosphere that is comfortable, a comfortable range of temperatures to live at. Runaway greenhouse effects are not great. Of course, an important question that we might ask ourselves is, Venus doesn't seem to have plate tectonics, but does it have active volcanoes? We don't have enough images of the surface to get a direct eruption, but we have seen volcanoes at the surface by bouncing radio waves off the surface. You can see these images here in the radio regime of these domes, and we attempt to reconstruct them three-dimensionally. Here's one of the tallest volcanoes on Venus, known as Mat Mons. And you can see here, they've sort of false colored the radio image, sort of to trick your brain into believing that you're looking at live lava. What you're really looking at is probably reflectivity of radio waves. And yes, probably recent outflows have slightly higher metal contents in them or something, making them more reflective. I don't exactly know the details of the science here, but these radio images sure show something that looks like lava flows. There have been some papers published that attempt to, they claim that they've measured little Doppler vibrations, sort of eruptions on the surface of Venus. And most people agree today that Venus probably does have active volcanism. We just don't have the imaging capabilities to really look at the surface of Venus in detail. Its atmosphere is thick and opaque, and it's hostile to the spacecraft that we want to land. So it's kind of interesting that our sister planet is still today one of the most mysterious of all planets in our solar system. Oh my gosh, I am totally running out of time here. One last slide that I want to cover, because it would be sort of a tragedy if I did not, is for us to just talk a little bit about the carbon cycle on Earth, because this is kind of an important concept in modern planetary science. And I'd just like to show you guys a little peek at a slide here. Normally I take notes on it, but I think today I'll have to skip that. And I just want to show you another great information graphic that really helps us understand, slide 43, why Earth is special and what happened to all of Earth's carbon dioxide. You guys will remember that one of our planetary atmosphere mysteries that I set up at the beginning of this lecture was, why does Mars have 96% CO2? Why does Venus have 96% CO2 in its atmosphere? And why is Earth's CO2 only at 0.4%? It's because of our liquid water oceans and the CO2 cycle. It turns out that if you combine carbon dioxide, silicate rock, and water, you can make a type of porous rock called limestone. And there are other examples of carbonate rock as well, but limestone is maybe one of the best. Let's look at a picture here, a high-resolution image of some limestone rock. There's one that I like more than others. And, they have limestone quarries around Rhode Island, but a huge fraction of limestone is actually bound up in things like coral reefs and other types of chitinous animal shells. I don't know if they'll be able to see this here, but sometimes you can actually see little bits of seashells cooked into this limestone rock. Limestone basically traps carbon dioxide at the bottom of Earth's seafloor bed. And let's walk ourselves through this cartoon here on slide 43. Okay, so first you have volcanism, and volcanoes are constantly going off on Earth and pumping out both water and carbon dioxide. Next up, we have CO2 dissolving in rainwater in our atmosphere. Just like Coca-Cola can dissolve carbon dioxide can dissolve itself in rain droplets. I think it's called carbonic acid. It's CO2 mixed with water creates a slightly acidic water, which then rains down on the plains of Spain and dissolves silicate rock down into the oceans. Think of the muddy waters of the Mississippi. All of that brown silt that you're seeing, that's silicate rock just being washed off of the continental surfaces. And once in the ocean, the CO2, the water, and the silicate rock combine to form things like limestone and other forms of carbonate rock. And basically, we've estimated that Earth has a Venus's worth of CO2 trapped in the seafloor beds. If Earth's oceans were to suddenly boil away, all of that CO2 gas would actually sort of, I don't know if the word is sublimate, but it would eventually be chemically released from those rocks and would find itself back in our atmosphere. Instead, Earth pushes those carbonate rocks along the seafloor bed down into subduction zones and keeps the CO2 circulating around in this carbon cycle. Now, which of these steps would you imagine, students, takes the longest? Which of these steps has the longest time scale associated with it? Volcanism, the dissolving of CO2 in the rainwater, erosion, the subduction of carbonate rocks. Where do you think CO2 spends its most time in this little cycle here?
Yes, the subduction.
Yeah, because remember, it takes something like a geological time scale to push this rock along the ocean bed. So it'll spend hundreds of millions of years trapped at the seafloor bed and a much slower, shorter time scale undergoing this process of dissolving in rainwater. And erosion is a very fast time scale. It happens over the course of weeks, months, and years. In any case, this is one of the reasons why Earth has maintained climate stability for hundreds of millions and maybe even billions of years, is because it just keeps a small, tiny amount of CO2 in its atmosphere, which perfectly regulates your temperature. Now, of course, observatories around the world maintain weather stations that monitor the levels of carbon dioxide in our atmosphere. And one of these famous observatory sites, of course, is the Keck Observatory on Mauna Kea. So let's take a little look here. I just have a morality tale for you. Let's look at the Keck Binocular Telescope, which is located on the main island of Hawaii on the Mauna Kea volcano. One of the reasons why Hawaii is still one of the greatest places on Earth to do astronomy can be seen in this picture right here. The Keck Binocular Telescope is a pair of 8-meter telescopes located about 8 kilometers up on Mauna Kea, and that puts these telescopes above the cloud layers. That means you never have cloudy skies on Mauna Kea because you're sitting above the cloud layers. Now, of course, Mauna Kea, I don't know if it's a completely active volcano, but Hawaii suffers eruptions all the time. And when you travel to these islands to do astronomy research, you usually have to spend all day on an airplane, and you have to spend all night at oxygen deprivation altitudes doing your astronomy research, and that gets you pretty tired. Luckily, there's some very delicious coffee that grows on the island of Mauna Kea, the Kona coffee beans. If you've ever been lucky enough to have yourself a cup of Kona coffee, it is especially delicious. And let's see if we can see the Kona coffee bean plantations. Coffee plantations. One of the reasons why Kona coffee is so delightful is these beans are growing in this very rich volcanic soil along the island of Hawaii. And I remember one of my fellow graduate students going on a trip to Mauna Kea to collect some data from one of the professors, and brought me back a bag of this freeze-dried Kona coffee right from the island. And I didn't think much of it until I brewed the thing up and had a cup of it. And I thought, oh my God, this has got to be the best tasting coffee I've ever had. So go to the store, get yourself a cup of Kona coffee. There's a reason why I'm telling you this. I want to show you guys a little slide here very quickly before we end our class today.
You can go to Hawaii too. A lot of the coffee plantations will like take volunteers that want to visit Hawaii, and you can stay on the coffee plantations and work, but they don't pay you. You can live in Hawaii.
Okay, that sounds fun in principle, but I bet harvesting all beans all day in the sun is actually some ass-busting work. So, but it's something to think about. And I guess as far as college student jobs go, it's probably not the worst one. I'll probably teach you a few things about life. Now, the reason I'm telling you that story about Kona coffee is not only to promote good coffee habits among my students, but also to tell you about this slide here. This slide is a measurement of carbon dioxide levels on the island of Mauna Kea taken at the Keck Observatory from the year 1960 to 2000. And you'll see that CO2 has a pretty low abundance in our atmosphere. It's only sort of at the parts per million level, maybe about 300 parts per million. Now, do you guys see this tiny little oscillation in the concentration of CO2? Those are changes in CO2 levels due to the growing cycle of the Kona coffee beans, which grow along the slopes of the volcano. So basically, when the plants are in bloom, they're absorbing a little more CO2 and expirating a little more oxygen. And when they're not in season, CO2 levels get a bit higher. And so this is sort of what nature is doing based on the levels of CO2 in the Kona coffee beans. Now, superimposed over that is this crazy dramatic rise where we see the levels of CO2 going from around 300 parts per million. And this graph, by the way, has been continued out to 2020, and it's continued to go up ever since then. Now, that's kind of messed up because if you remember one of our earlier slides, Earth gets a net change in 30 Celsius degrees due to the small amount of CO2 that is in our atmosphere. And okay, so this is maybe too simple an argument, but in a way, if you've got a change in 30 Celsius degrees equal to something like 300 parts per million, that's sort of suggesting that every 100 parts per million change in CO2 you're going to get is going to give you something like 10 Celsius degrees. Now, it turns out to not be quite that simple. It's not a linear relationship, but it does give you the heebie-jeebies if you think about it, because a change of 300 to 400 parts per million, that's an increase of 33% in our CO2 levels. And sure enough, global planetary temperatures have actually been rising due to this change. Now, of course, people debate what the cause of this is, but I'll tell you what's not causing this increase in CO2. It's not the Kona coffee beans, right? That's probably man-made carbon emissions that are producing this. And the census, the global consensus of the scientific community is that man-made climate change is real. Now, the thing that really gives planetary scientists the heebie-jeebies is if there is a Venus's worth of CO2 trapped at our seafloor bed, you could imagine a situation where when global temperatures begin to rise, you could increase the evaporation and the fraction of water in our planetary atmosphere, and water is itself a greenhouse gas. An increase of CO2 plus an increase of water in the form of vapor could lead, in theory, to a runaway greenhouse effect, and we could end up living on a planet that in the future was closer to Venus than it is today. Our CO2 cycle is strong and probably would return temperatures to their global average eventually, but it might take a geological time scale for that to happen. And you don't want to throw Earth's temperature out of balance for 100 million years. That would not be good for the apex predators on planet Earth, which is us, the human beings, right? Who knows? In the future, we could open up our planet to the evolution of a new species like hyper-intelligent dragonflies. Maybe they're the creatures that deserve to inherit our planet. But unless we clean up our act, it's probably not going to be us. Okay, I think that's about all the time I have for today, and I squeezed as much as I could in. On our next, I guess, and final class, we will cover all things Jovian, including the excellent Jovian moons. Today's lab is on an exercise where we will measure the mass of Jupiter by studying the rotation of moons using a little computer simulation. That computer simulation is a freeware program called the CLIA Revolutions of the Moons of Jupiter. Now, originally I thought that maybe I'd try to get all you guys in the studio audience to download this and take the measurements, but I think that's going to turn into a clusterfuck of no good. I think the way we're going to do today's lab is you guys are going to all download the exercise, the Mass of Jupiter lab, and I will run the simulation from my computer and we will collect the same data together. I think that's the best way to make sure that the time it takes to do this lab doesn't get out of control. So I think we can do this well under an hour. Let's take a little iced tea break. Are there any questions before I grab a refresh on my iced tea?
Yeah, what page is the lab on?
It's exercise number 6 in your lab book. But as I mentioned earlier, Angel, the pages that you really need, if you want to save printing paper, 6.5, 6.7, and 6.15.
Okay.
Those 3 pages are at minimum what you need. I just printed out the whole thing because I was lazy. Okay, so we all want that little 5-minute break, yeah? We like this? Okay. Let's take a pause. I'll stop the recording.